Hello, Ketna, I'm audible.
Yes,
Alright, Ketna. So, what we discussed in the last class, could you remember that? Yeah, Ketna, which topic we discussed in the previous session? Be louder, let me know which topic we discussed in the previous session.
LS,
Velocity?
LR circuits.
LR circuit, makes sense. Okay, fine. Okay, I'm just sharing my screen. Please let me know if you can see that. I've shared it. We did about growth of current in LR circuits. Okay, the current part. Okay, now let's start with the DK. DK of current, okay? In LR circuit, yes, in LR circuit. So look, DK of current, okay? Now what we are actually doing is simply look. If you could remember the previous case, we discussed one problem where you had an inductor in between, and this was a circuit, right? It is not connected right now. Assume I'm giving this condition, okay? There's a page which is closed, open right now. You know there is some current flowing in this circuit in this case, right? Now what happened is, if you look at the condition, the current flowing across this inductor is some value I, right? Assume that is I. At this instant, the moment I'll remove this circuit and I'm going to close it. So now situation comes with you is looks like this. I'll just make it once. So you have an inductor. This is connected with a resistance. Okay. At this instant, the current flowing in this, maybe you can call it as I. Right? Okay. Now what will happen? You know this current was a result of previous session, but now you have removed that potential. Okay, you have removed that potential. It means removing that potential means decrement of the current. Okay, so what actually is going to happen if you look at this circuit? Because this is decaying current, right? This is decreasing current. So what will happen? This inductor is going to produce an EMF in this direction. Okay, how is this going to happen? We'll see. So you can, let's say this potential across current is going in this way, right? So let's say you can call it as I times of R minus times of E, sorry, what is current EMF? LdI by dt. Okay, I was supposed to write it in a positive term, but like it was going in this way. So if you write in this manner, it will be like this. What about this di by dt? If you look at this, it would be just a second. Yeah, Ketna. So this is the condition we have so far. Another way of seeing the same condition is let's remove it once. You know very well that when current was flowing across this inductor, so what is the energy across it? You can say that this inductor is storing a potential energy. So energy stored in that is half Li square. Okay, this is one more thing you can think of it. There's two ways how we can solve the same problem. This potential energy is going to decrease by the time and it is going to get converted to something like I square RT. Understood? Because current is going to flow and decrease by the time. So either way we can go with it, but let's come back to our previous situation. This this results we have got through the applying simply KVL rule. Okay, current voltage rule. If you look at this condition, let's take it to other side. It will become L di by dt in negative sense is equals to I times of R, and here you go with an integration of dt. This I will go downside, so it will be like simply integration we are going to do, nothing else. Okay, so it's integrated. If you see carefully, this current is going from some maximum current I naught to some small current I. Here you are going from zero time to some time t. Okay, so if you just look at this condition, what you are going to get negative of log final I by I naught. Look, you should know this integration part. Okay, and here you are going with RT. Clear? You can put this negative to other side and this answer will become I is equals to I naught e to the power minus t by r. If you think this answer is correct, actually it should be L should be at the bottom, okay? Because there is an L, it will go to other side. Let's keep it here. L and this becomes LT. So what is the final thing? This is something like T by tau. This is the answer you are going to get, okay? Now if you just compare it with the previous case, what is the current in this circuit at time t is equal to 0? Put the value, you are going to get current is equal to I naught. Current is equal to I naught, okay? So this is the equation for decay in current when you are talking about LR circuit. Okay, here if I have to make the graph, how it will look like. So the graphical representation of this is something like this. Look, previously we had this kind of condition saturated at some after some time. Here we have this kind of condition. Okay, so this is decay of LR current and let's take it to the here it is going to get at the this is growth. Okay, so that's the thing. Here you can see it is going from some top value I naught to approaching towards the zero in this DJ case. I have actually merged the previous case and this case. Okay, I have merged both of the case in a single graph. So kids can just look at this and let me know if you have any doubt.
No,
No doubt, right? Yeah, so Kirtana, look, this is one thing we have discussed. Now, what if I ask you calculate power? Power. So you know that power is nothing but I square R, right? So very simple idea. Power across R is nothing but I naught square E minus 2t by tau and the power. So this is the power. You can see the power is consumption is also decreasing with the time. Again, if you look at the graph, this graph will look like power divided by time. Alright, so look at this. This is kind of a graph you're going to get for power versus time. Okay, this is the graph going to. Okay, Kirtana. So if you're clear with these two concepts, we can actually move to the problem. We'll solve some problems and yes, we are done with this concept. So let me know if you have any conceptual doubt in this part, in this particular part, which we have done so far. Kirtana,
No,
not okay. Okay, so I'm going to give you a problem, and so you are supposed to solve it, as you don't have it out. So assume that. So look, Kirtana, in this problem, I think Mike is on this. Yeah. So basically, this is a problem, right? You know very well that because of this case, current will start flowing from trees. Assume I'm right now I'm talking about the time t is equal to 0. At this moment, the current will start flowing. By the time the current will reach to one steady state, okay? There's a time when it is going to reach a steady state. I'm going to insert a rod. Okay, this is a rod I'm going to insert. A rod. Okay, look at this. So after steady state, a rod is inserted in this loop or the coil or the solenoid in inductor. Okay, inductor. Now calculate the current as a function of time. As a function of time. This is what you need to calculate. Look, earlier the inductor was very normal. Okay, follow inductor something. There's nothing inside there. You let the current grow from zero to some very higher value, and it reaches to steady state. When the condition was in steady state, I inserted a rod having relative permittivity around mu r. Okay, relative permittivity mu r. In this case, you need to calculate after insertion. You need to calculate the current in this circuit with respect to function of time as a function of time. So just calculate and let me know the answer. क्या गौरव मेरा फर्स्ट ईयर का रूममेट क्या वो तो अकेला ही है राया राया है रुद्र है लक्ष्य तीनों खाली है फिर ठीक है तो तेरा लक्ष्य का जमेगा नहीं वो मैं जानता हूँ पता है तो मेरे को पता है Yeah, Ketna, look, have you got the answer for this one? Ketna,
The
I don't hear you. Alright, so Kitna, if you have solved it, please let me know. Otherwise, I'll solve it out. Alright, Kitna, look, I'm not sure of whether you have solved it or not. Look, a very simple idea is that you know that one of the main property of this inductor is it never allows a very sudden change. Okay, it never allows a very sudden change in flux which is passing through this. Okay? This is something which happens. So assume that before rod insertion, if I ask what is the flux, L times of I, we are very clear. What is the value of L? L is something mu naught, I, anything else? Yes, pi r square, anything else? Number of turns square, and L. This is some formula which comes up with respect to this thing, right? N square, mu naught pi r square n square L. Does it? No, sorry, current should not be there. It's not. It's not there. Okay. So this is value. Now what happens is, over the moment you have inserted a rod in it of some mu r. So what happens? This inductor change because this mu naught changes to mu naught times of mu r. So this is something. So if you see carefully, L dash, which L dash comes out as L is basically mu naught. Sorry, keep it here. Mu naught r square n square pi L. Okay. After insertion, what happens? Look, I told the moment you change, flux is not going to change. It means flux will remain same. To keep the flux change, assume that new self-inductance is L and current is I dash. So you know this both should be equals. Before and just after flux remains same as inductor opposes sudden change. Look, I'm just talking about the sudden change. Okay, sudden change. So new inductance L dash is equals to mu naught mu r square n square pi times of L. So you have got something like mu r times of L. Okay, something which you have got. Now, if you just look at this condition carefully, I am going to switch it over here. So you are going to get mu r L is equals times of I dash is equals to Li. So you have got I dash is equals to I divided by mu r. Now what happens is now this condition looks like this is mu L dash. Here the current passing is I dash. Okay, and okay, there's a resistance R. So this is the battery. Now you know whatever the condition at the end of the day, this inductor is going to vanish. At the end of the day, it is going to act as a single wire or something, right? So current final should be equals to I naught in a steady state. Okay. Now, if you see this is divided by mu r, it means it is lesser. Now, at this moment, this current will start growing. It will be like currently I am I dash. Now it is going to grow from this value to some I. Okay, makes sense. We can now apply the same condition which we had in the previous case. Okay, a very general condition we can apply. So just this case, here you have current E minus, this is, what is this now? Mu naught. Not mu naught actually. This is L di by dt. Is it? No. There should be mu naught. Negative times of IR. Okay. If you look at this, it is like growth in current, right? You know what is the formula for the growth in current? That is I is equals to I naught, okay, 1 minus e to the power minus t times of L by R. Here you will be having mu naught L by R. Okay? This is you are going to clear. Generally, we say you are going from in the growth of the current when we generally write the formula. Uh, Actually, there should be one more parameter over here. When you integrate it, you got something like e minus IR. You e minus IR. So here you got e minus I naught times of R, the final divided by I e minus this. In this case, I'll be having I dash R. Clear? This is more parameter I'll be having. So if you want, I can actually go. Let's go in very detail integration. So it will be like e minus mu naught R L d I is equals to I R dt. So this goes on. Actually, अच्छा तो नहीं लग रहा है तुमको alright, Kidna. So did you understood the integration till this step from this step to this step? Look, E was nothing but I naught R. Okay, the maximum current you can ever have. So you can simply rewrite this thing as I naught R minus I by R divided by I naught R I dash. R. Okay, this is something we are supposed to get clear. Okay, so just multiply to that side. You are going to get I naught R minus I R is equals to I naught R. Let's call this as something A. Okay, now let's call this as A. Why? Because I'll just take constant at the end of the day. I dash R times of A. So if you see what I wanted is I want this I to be one side, rest of them to other side. So let's keep it other side, rest of them to this side. Okay. So IR is equals to I naught R, this to other side also. So this becomes minus times of I naught R A. This goes other side, so it will become plus I dash R. No, add it means. If you see, like two options are very predictable. What you can do is I naught R, take this negative common. The moment you do this, minus, you'll be having RA to take common. Or another way you can take is, okay, let's do one thing. Let's take RA as a common instead. Okay. So you'll be having this negative you are going to take common out of it. So you'll be left with I. Do one thing, take R as a common out of it. So R got cancel. Actually, R you can remove it from the whole equation. You will be left with I naught minus I naught times of A plus I dash. Okay, so here I can have a clean picture out of it. What is that? I naught 1 minus A plus I dash. Something like this. Or you can rewrite it as I naught 1 minus e to the power minus TR divided by mu L plus I by mu times of I naught by mu times. So what is I naught? We have already calculated. And what is A? A is nothing but TR divided by mu naught. This is what the equation will come out. Do you really need to remember this? No, you don't need to remember this. You just need to understand the concept, understand how you are supposed to do any kind of problem if you encounter. Okay, that's what you need to remember. Look, do one thing. Go and read out whole steps one by one carefully. Let me know which step you are having doubt. Okay, do it once. Don't say that you really remember, understand this thing because I know you can't. Kedna, look, if you understand it, please let me know. Okay, so that I can move further. Kedna, did you understand it? Should we continue or you are still reading it out?
I'm reading.
Okay, just read it and when you are clear, you are comfortable with this kind of problem, let me know, we'll move further.
clear, sir.
It's clear, right? Okay. Do one thing. I'm giving you one more problem. Although I was supposed to give, we were supposed to discuss about the LC oscillation from here after. But okay, let's do one concept and we'll end the session today. Okay. This is last concept from today's session. So look, just like we did, you know very well that we have done RC when we are talking about the capacitor. LR we have discussed just now. Okay, we are done with LR. Now, what if I include instead of R and L, C and R, what if we keep L and C together? What does this mean? Let's see. LC circuits. Look carefully. In case of inductor, this isn't store energy storing element. Okay. In case of inductor, this also stores energy. How much energy they store? This stores how much charge it has. So charge is like Q square by 2C, right? This kind of energy it stores. What about this? This stores half L I square. How much current passing through this? Okay. This is what the energy is stored in general. So can we create an LC circuit? Yes. Assume that I'm having this kind of circuit, LC oscillations basically we are going to discuss about. And here you have an inductor. Okay. This is L, this is C. Positive, positive. We don't know whether it's positive or not negative. Okay. It's your choice what you wanted. You wanted this to be completely charged or this to be completely charged. There's a one way to go with, okay? Or so like if we say if I'm saying this capacitor is completely charged, at that means I'll say whatever the charge is there, that is the net energy it has. Current right now in the circuit is zero. Okay, and it will start growing by the time. So look, assume that let's say you are having mm, initially, let's say capacitor is charged with Q. Okay, Q is the charge on the capacitor. So you know very well if Q is the charge on the net capacitor, electric field might be this. So this is positive, this is positive. You can see that this is acting as a battery, right? Potential. What is the potential? Uh, that is V is equals to Q by C. That is the potential. You know because of this potential, there will be small charges will start flowing, right? Charges will be flowing. So due to that, some small current I will be also be flowing. Right? Assume that at some time t, okay, the potential like what I can say, the potential the charge remains on the circuit is Q. Charge remain is Q. Okay, and current flowing is I. You know, current flowing is nothing but how much charge is flowing by the time, right? So this is what we can actually think of it in a one way that current is flowing. So you can actually say let's use a KVL loop. If you go with a KVL loop, what is the potential across this? That is Q by C minus current is going in this way. So you can actually keep it as L d I by dt. Understood? This is what we are going to do in this case. If I ask you what is current over here, so current is nothing but charge flowing through the circuit, right? If I ask you what is the current, current is nothing but the charge flowing in the circuit. So this was Q actually, and I is equals to Q by C. Okay, sorry, that is dQ by dt. So you can actually see that Q by C minus L d by dt. What is this? Dq by dt. There is one more point because charge is decreasing. Charge is decreasing by the time. Understood? because potential is decreasing more. So I will come out as this will come out as minus dq by dt. Okay, negative. The rate of change is negative. So you got q by c plus L d to q divided by dt square. Is this clear till now? Kirtana, let me know if you are clear with this.
Yes, sir.
Clear, right? So look, can we rewrite it another way? Yes, that is 2 dq divided by dt square plus, okay, sorry, L is also there. You can actually rewrite it as q divided by LC is equals to 0. Now, how to solve this equation further on? So for this, I wanted to take you back to your SHM classes where we have stated one thing that there is an equation x is equals to, sorry, yes, amplitude times the sine of omega t plus theta. If you could remember when we write the equation, okay, if I just do a double differentiation of it, how it will come up? Just do the double differentiation. Dx by dt, this will result you around a omega sine omega, sorry, it will be like cos, what is it, omega t plus theta, but something, remove this theta, I don't even need this theta for now, or let's keep it as theta is fine, okay. If you do again it, you get something like a omega square negative sine of omega t plus theta. If you look at this carefully, this a of sine theta will result to what, d2x dt square, so minus omega square, what is that, x itself. So can you see this? In my equation, I have t2. If I replace this x with q, isn't it the same thing? Here I am getting, if you take it this side, I am going to get omega square x. Can I relate it? Yes. This can be written as x. So equation 1, equation 2. Relating with equation 1 and 2. What you are going to get, you can simply look how it is working. It is basically SHM equation. This is also an equation of SHM. Can I say that by relating both? Omega is nothing but under root L by C. Yes. In this kind of oscillation, this is coming out. Also, you can write the equation for this as this x q is equals to q naught, that a is the maximum, right? Omega is what? You don't know. Sine times. So what is omega? Omega t plus theta. Some theta, okay? We don't know what is the theta, and you know the omega value is this, right? We are clear with this. This is now what this theta is defining. This theta is telling at which phase you have started the thing. For example, look at this carefully. If you could remember, in my case, if I put my theta, if you look carefully, when time is equals to 0, my charge q was q naught, the complete charge, right? So you can simply say, sir, if I put this q naught is equals to q naught sine omega t plus phi comes out as 1. Yes, sorry, because this get cancelled. So sine plus phi comes out as 1, which means this comes out as sine of omega t plus phi. This thing is coming out as a pi by 2. Understood? Inside thing is coming out is equal to pi by 2. So what we can further write it as, you can also call this as omega t plus phi is equals to pi by 2. So this phi comes out as omega t, look, sorry, pi by 2 minus omega t. Something this way you can actually rewrite it. I suggest you to do this. Clear? So if you go back and put the value for this, you are going to get something like theta is equal to pi by 2. Sorry. And also one thing, this is the thing, and time is already you have kept is zero, so this 5 will be 5 by 2. So you can see that this Q equation comes out as Q naught sine of omega t plus 5 by 2. This results around Q naught cos omega t. Clear? Look, now what happens is, the moment you put t is equals to 0, Q is max. Clear? That's how you're supposed to solve these kind of problems. This Q oscillations can be written in either way. Either you can say start with omega t plus phi. This phi is going to represent which state you are in. Okay, if you carefully locate it. For example, in this case, if you put Q is 0 at the very start. Okay, if you put the Q is 0 at the very start, what will happen? Time is already 0. This theta will come out 0. It means sine omega t. Now, if the equation comes out only Q is equals to Q naught sine omega t, what does this mean? This means that when at the very start your inductor was charged, not this. Okay, that's how you have to solve these kind of problems. So let me know if you're clear with it or not. Yeah, clear. We are done by this. So let me know if you're clear with it.
Yes.
Clear, right? So Kirtna, that's all for today's session. Good. I'll end the session very soon.